So we're now beginning the second part of this course, which is on pre-quantum mechanics, and in particular today I'm just going to talk about black body radiation. So if you've ever looked at a stove, an electric stove, the burner on an electric stove, you notice when it gets hot it starts to glow right here. Or better yet, suppose you're looking at a kiln, a pottery kiln, right here, and it's hot on the inside. And you open up the door and you peek in and you'll notice that it glows inside. How is that light created? How do you even make light? Well, from electromagnetism, Maxwell showed that you create light by accelerating a charge. And the most efficient way of creating light is by just taking a charge and just shaking it up and down. Put it on a spring, shake it up and down, right here. We call this dipole radiation. And Maxwell showed that you get some wave traveling out. We'll just say this is the electric field right here. There's also a magnetic, but I'm not going to show that. Well, and this wave we know travels at the speed of light, and we have one wave equation, which is the wavelength times the frequency is the speed of light. We're talking about in a vacuum right here. Okay, so how do you measure this radiation coming out if you peeked in right there? Well, you could have, say, some sort of a detector right here. Say this is my detector. Detector. Has a little opening here. Say it has an area A. I happen to have a detector right here. So here's the detector, and I can open it up. There's the area A right there. And in this one right here, this one creates an actual photograph of it. And there should be one on the screen now, and you can see that the hotter it is, the whiter it is, right? And so what is that actually measuring as this radiation comes in here? Well, what they're measuring is they're measuring the energy per second coming in. Light has energy right here. This light's going in. Light energy per second per area of the detector area, because if you had a bigger area, you'd get more, per frequency range. These detectors only work over a certain frequency range, per frequency range. Let's say delta F. They work for over a certain frequency range right here. Okay, and I'm going to give that a letter. We'll call that letter, say, J, right here. That's what we're going to call this right here. Okay, and if we were to, you might say, well, so what's happening here? These charges on the walls of the kiln, we'll call this a kiln, say, are shaking up and down, creating radiation. Over here, they're shaking, creating radiation all over, and we peek in, and some of that radiation leaks out right there. So, if we come over here and say we plot out, this is the frequency of the light that we're detecting right here. And on this, we're going to plot that little J right here, this J, which is how much energy you're getting per second per area over a certain frequency range. Well, since we only get frequency over a little range, we're only going to get values between here and here. So this is the region where we're getting. And so what we're going to get is, we're going to get something that looks like this right here. This is how much energy right there. That's how much energy we got. That was the energy per second per area per this little delta F. delta F, right there. Okay, so that's what this value is right there. Now, better yet is, instead of asking what the height of this is, a better thing would be, what is the area? How much area is in here? What is this area right there? Well, this area should just be the height times the width right here. So that would be J delta F. So J delta F right here shouldn't have any delta frequency here. Delta, remember this was a delta frequency. Why? Because that would cancel out this and you just have energy per second per area. Well, energy per second is just a power. So this would just be a power per unit area. Power per area. So that J delta F is just going to be how much power is coming in here divided by that much area. Remember, that's between F and F plus delta F. So this is between F and F plus delta F. Right there. Now, this is kind of this radiation coming out of here is kind of a special radiation. Right? Why? Because when you have a surface here, radiation can come off that surface two different ways. One way is by just reflection. That is, radiation comes in, pops back out. We call this reflection. Well, there's another type besides just reflecting right here. Radiation could come in here, get absorbed, and then re-emit right here. You can't just, so here you absorb, and here you re-emit. And you notice, what's the difference? It looks the same right here. There's no energy loss on the surface here. This one, there's energy loss. This absorbs the light and then re-emits. And for this thing to be in equilibrium right here, thermal equilibrium, if you're a good absorber, you better be a good emitter. Otherwise, this surface would just keep getting hotter and hotter. So the rule is, you're either good at these two things or you're good at this. They're mutually exclusive. You can't be good at both. Well, what we want to look at here for our radiation is we want ones that are just good at this and just horrible at that right there. Well, you'll notice if we look at something like, say, this blue pen right here. This blue pen, the white part of it is just reflecting all the colors on it right here. And the blue part of the pen is reflecting all the blue and none of the others right here. The only one that's reflecting none of the light, I guess, is this cap right here. None of the visible light that reflects off of it, it's all being absorbed and then re-emitted. So usually we call this a black body, but black bodies aren't necessarily black. They're only black when they're cool. When you get them hot enough, like the inside of a kiln or the burner on an electric stove, when you get above a couple of maybe over 600-700 degrees Celsius, they start to glow. So black body is only meant at low temperatures. They're only black at low temperatures right here. Okay, so now, how do we make almost a perfect black body? Well, we can almost do it something like this, with a cavity right here. Suppose we have a box right here. It could be a kiln right here, but it's got a little opening on it right there. And this thing is hot inside there, so I'll just draw it by a flame right here. So this is hot in here. The atoms are jiggling around, creating all this light right here. here's a little opening right here. Now, some light can get in right there. But when that light gets in, most likely it's not coming back out that hole right there. Why? Because the odds are just too slim that it's going to come out back out that same hole. Most of that light that's coming out is all this stuff that's generated inside, because this is much warmer right here. So this is kind of a nice black body. Matter of fact, you can buy these devices. They're meant just to get this black body spectrum. And what you'll notice about this spectrum, that is when it's all this and none of this, is that the spectrum coming out has nothing to do with the material. It has nothing to do with what this is made out of, right here, which is kind of strange, that it's just nothing to do with the atoms right here in the material. So that's what we're going to call black body radiation, no reflection, right? Well, this was one piece right here, but now I want to get the whole spectrum. So what do? Well, you get another detector that works a different range right here. Maybe it works from here to here, and you measure how much energy you get per second per area right here, and you get another one right there. Or you could do it over here. Maybe you get something over here, and so on. And you could make up a full spectrum. But this is just too choppy. It doesn't look very exact unless I were to make this thing a little bit skinnier right there. Well, let's make our delta F smaller so it looks a little smoother. How small do we want to get? Well, why don't we just let delta F get really small, infinitesimally small, all the way down to DF right here. So now these would be really skinny, and hopefully we get a nice spectrum. And if we do that, so now this J right here, it's going to be, it's just going to be a function of the frequency and the temperature. It's going to be affected by the temperature because you get a little bit hotter. It's not going to depend on the material or anything else. And I need a DF. Why? Because I want the area under the curve versus frequency. So this right here would be, again, a joule per second, an energy per second per area within the range F and F plus DF. Right here. And what you would get is you get something that looks something like goes up and comes back down right there. If you got it hotter, it would shift it and make it a little bit bigger. Kept getting it hotter and shift it and make it a little bit bigger. But the shape of the curve would always be the same. It would just be shifted and grown right here. Okay, so again, this spectrum is independent of the material of the object. It's only a function of the temperature and frequency. Okay, but the only thing is most people plot this out instead of in terms of frequency, they plot it in terms of wavelength. Remember, we already said what wavelength was. Wavelength is equal to C over the frequency. So if we plot it out versus the wavelength, really what it does is it's just going to, it almost kind of flips it around right here. So it's going to be something that looks like this right here. And we'll see some spectra in a minute right there. Okay, so the only thing is, as you get hotter here, you shift this way, hotter. Over here, if you get hotter, you shift this way and up, hotter. Everything is a little bit backwards, right here. They're reciprocals of each other, right here. Okay, and so there is what the only thing is you have a DF in there, and if you wanted to know what DF is, since F is equal to C over the wavelength, DF is just the derivative of that. That's lambda to the minus 1, so that's minus c over lambda squared d lambda. The minus is only because it flipped right here. So, okay. Now, the big problem in this right now was they could not derive this formula, this spectra. You could not derive it, at least with all the known laws of classical mechanics. They could not derive this spectrum right here. But Wien, he empirically, by experimentation, noticed that, you know, this corresponds to this is the maximum wavelength right here, the peak of wavelength max right here. It's the wavelength where you get the maximum amount of radiation. If you multiply this by the temperature in Kelvin, you got a constant. That is, if you came a little bit, if you heated this thing up and you got the peak over here, the peak maybe comes over to here, the wavelength got smaller, the temperature got bigger. So if the temperature got twice as high, the wavelength would get twice as small. Right? So this is called Wien's law right here. The peak wavelength peak, times the temperature is a constant. Okay, so anytime we finally derive this equation, it better give me that right there. Okay, and then the other one is Joseph Stefan said that, you know, if you integrate this to get this total area, now he did it empirically, not by integrating any curve, because they didn't have the equation of the curve. Stefan, Joseph Stefan, S-T-E-P-H-E-N, says that if you integrate from 0 to infinity of, remember this is the area because you're multiplying it by df, j f t df, well, then this just becomes some constant times the temperature to the 4th power. We call this big R. It's the total radiated power out of an object, because you're integrating all the energy out of all the frequencies right there. So, and this constant right here is actually called the Stefan Boltzmann constant. The reason why it has Boltzmann's name on it too is because he actually derived this, R equals sigma t to the 4th, from E and M in thermodynamics. So he was actually derived it. Stefan just got it empirically. Okay, and so this is the constant. You probably get this in a different class right here when you're talking about thermodynamics and radiation. You get this equation right here, where that sigma, that Boltzmann's constant, is actually 5.67 times 10 to the minus 8 watts per square meter. Remember, that's my units of J. And then I need a Kelvin to the 4th to get rid of this Kelvin to the 4th right here. Why? Because what is this? R is the integral right here. And so you're integrating out this. And so you're integrating this over all the frequencies. And that's why you got a power per area. Okay, so now I just wanted to show you here we have if we wanted to look at it for the sun right here. So over here, this is actually the solar spectra, and you can notice the gray curve right here is a perfect black body spectra associated with 5,250 degrees Celsius. You notice the sun, which is the yellow, is very close to that black body spectrum. The red section is actually what makes it to the surface of the Earth. Now, here, the peak of the sun is right at kind of yellowish green. That's why the sun looks yellow right there. This is actually the visible part of the spectrum right here. Over on this side, the ozone layer blocks most of the yellow part over here, and we hardly get any UV, which is good for us. And then over on this section over here, the infrared is mostly blocked by water vapor in the atmosphere. So if you're going to make an infrared telescope, you're not going to be able to look in these regions right here, at least not a surface ground telescope, because they won't make it through the atmosphere. Maybe in this region and this region you could right there. Okay, so this is the radiation for the sun right here. Again, it follows a black body spectrum. If we look at the black body spectrum for the Big Bang, the Big Bang happened 13.8 billion years ago, that bright flash, and it has now expanded out and stretched and cooled. And if you take a picture of the smoke left over from the Big Bang, it looks like this right here. Now, it should just be a white sheet right here, because it should be very bright. And the only thing is, first of all, the reason why it looks color-coded right here is because they've made a big contrast right here. This is a little bit cooler. That's a little tiny bit hotter right there, the red parts. But it's such a small amount that you would never notice it right here. The difference between this and this is, between the blue region and the red region, is probably about 1 part in 10,000. So if the blue part was a plateau, a mountain plateau, this little red part here would be like a little person standing on top of this mountain right here. It's not a very big difference. This is the radiation from the Big Bang. And if we look at the spectrum of it right here, the blue is a black body spectrum, perfect black body spectrum. And you can see the little red dots are the actual data. This is from the Kobe satellite right here that looked at this. So there are a lot of objects out there that are black body, which means they don't reflect, right? Remember, they just emit. So on the next lecture, we'll go through how Raleigh and Jeans tried to derive this equation right here. And so they took a crack at that derivation. So that's what we'll hit on the next one.